Hi folks, so we are still in Module 9. We are doing the second practice in Module 9, which is all about inference on a single proportion. We're doing hypothesis tests and confidence intervals in this module. All right, so Mendel's first law of genetic inheritance states that crossing dominant and recessive homozygote parents yields a second generation made of 75% of dominant trait individuals. When Mendel crossed pure breeds of plants producing smooth peas and plants producing wrinkled peas, the second generation, F2, was made up of 5,474 smooth peas and 1,850 wrinkled peas. Do these data provide evidence that the proportion of smooth peas in the F2 population is not 75%? So what we're looking to do is test that the proportion, so we're using a proportion now, so remember we use P, is or is not 75%. And you can write that in decimal or percent form. We're going to need the decimal number, so I typically write it in decimal form. So our alternative is not, and our null hypothesis is the equal statement. Remember, the equal statement always goes in the null. So for the test of the proportion, the test statistic is Z is equal to our statistic, which is P hat, minus our parameter, which is P naught, that's the value in the null, divided by the standard error for the P hat statistic. That standard error is the square root of P naught times quantity 1 minus P naught over n. All of that stuff is under the square root sign. All right, so to be able to do this test, we need P hat, which is x over n. And remember, we can either have P hat or we can have x. We can have either one of those. We're also going to need n for this test. And then our conditions for this test, there are a lot of them, remember. The conditions for a one proportion z test are that we have a random sample, that we have a binomial variable, and specifically we have to have two outcomes. We have to have independence. We have to have n is equal to a number. And then the proportion has also got to be equal to a number, but we satisfied that by writing it down in the null. And so those are my three conditions there. And then I also have to satisfy the condition of normality to use the normal approximation. And that first condition is that n times p sub 0 is greater than or equal to 10. And n times quantity 1 minus p sub 0 is greater than or equal to 10. And I have to satisfy all of those things. All right, so let's try to figure this out. So first of all, we have 5,474 smooth peas and 1,850 wrinkled peas. Do these data provide evidence that the proportion of smooth peas is not 75? So we're interested in smooth peas, so that's my x. That's 5,474. Guess what? We don't have n in this problem, but we can get it. So the smooth peas, there were 5,474 of those. Wrinkled peas, there were 1,850. And those are the only two kinds. So if I add those two numbers together, I get 7324, and that's my sample size. So I have x and I have n, which is all I have to be able to plug this into my R program. So now I need to satisfy my conditions. So the first one is random sample. And really, this is a really big question mark here. We don't actually know. An experiment was done, so we can probably assume random sampling. Experiment, so probably. But I don't know for sure. We're just going to put a check mark there because remember, sometimes in biology, this one's ignored. Independence just means we have to have a much larger sample size. Well, there are tons of peas produced throughout the year. We either have wrinkled or smooth. There are only two outcomes. The sample size was 7324. And so that condition of binomial is met. Normality now, we have to have 7324 times 0.75 has to be greater than or equal to 10. Well, if I do that math, I get 5493. That's much bigger than 10. And then I need to do 7324 times 1 minus 0.75 or 0.25, and that is 1831. And so both of those are way bigger than 10. So normality condition is met. So we can use the normal approximation. So now I want to go to R and get my test statistic and my p-value. And typically my test statistic would be a z-test statistic. But remember that R doesn't do this normal approximation using the normal curve. Instead, it uses a different distribution that we're going to get to soon called a chi-square distribution. And we also need our p-value. So let's move to R and do that. So let me close this down. Go to R. And I'm going to do a one proportion z-test. We need to put in x, n, p, which is our null value. We need to put in the alternative, which is either two-sided, greater than, or less than. And then we do have to include this thing correct equals false. There is a correction factor that some books use and some fields use called the Yates correction factor. We're not using it here, so we're just always going to use correction factor equals false. So you do correct equals false. It doesn't really matter whether you use it or not. That'll be something that you'll find out if you ever do this test in your field. All right, so we're going to do the prop test. So prop test, X is our smooth P's, yep, 5474, comma, N, which is 7324. Notice I don't have to set those equal to something. But then for the proportion, I do have to do P is equal to whatever's in the null, which is 0.75. It does have to be in decimal form, comma. I have an alternative that's two-sided because I'm doing not equal to. And then correction equals false, so I do correct equals false. So I need to run this code. And when I run this code, I get this output down here. It's a chi-square test statistic, which is 0.26. And then my p-value is 0.6081. This should not be a surprise to you guys because this particular experiment has been proven over and over and over again throughout time. And we're getting the same results everybody else typically gets, unless you just got a weird sample. So the chi-square test statistic is 0.26. The p-value is 0.6081. And so now we make our decision. Same way we've made them for the last few tests. P-value compared to alpha. P-value is 0.6081. We don't really care what alpha is. We weren't told what to use, so we're going to use an alpha of 0.05. I don't know why I wrote it twice there. This p-value is large. In fact, it would be large. It would be large no matter what our alpha was, a reasonable alpha level. So we're going to fail to reject Ho. If we fail to reject Ho, remember, we have to keep it. And if we keep Ho, there is not evidence for Ha. So our decision here, or our conclusion, is there is not evidence at any reasonable alpha level. And notice I say that just because our p-value is so big, and I'm going to include the p-value here. P-value is equal to 0.6081 to show that P is not 75%. Remember, we can never prove Ho. We just are trying to prove Ha, and there was no evidence for that. All right, let's do our next problem. So this one we won't need R for. Compare the hypothesis test and confidence interval. A recent poll shows that 48% of Southwest Virginians support the pipeline project with a margin of error of 5%. Representatives in Southwest Virginia are saying that less than half of us support the pipeline. Support or refute this statement using the numbers above. So we know that our confidence interval is our statistic plus or minus the margin of error. And we have our statistic, it's right here. And we have our margin of error, it's right here. So p hat is 48%, that's our statistic, plus or minus our margin of error, which is 5%. And I can do that math. 48% minus 5% is 43%. That's my lower bound for my confidence interval. 48 plus 5 is 53%. That's my upper bound for my confidence interval. And I'm asked to support or refute the statement that less than half of us support the pipeline. So the null hypothesis is that the proportion is equal to 50%, and the alternative is that less than half of us support the pipeline. Remember that the null hypothesis is truly the opposite of that. So it's greater than or equal to, and that's just our status quo. It's where we have to stay. So you may want to sort of keep that in mind. So I'm going to graphically illustrate this down here in part B to answer the question. So my confidence interval was 43, which is here, up to 53, which is 51, 2, 3 there. And so my null hypothesis, or my true mean, is somewhere in here. I'm saying that the mean is somewhere between 43 and 53. And so to be able to answer the question, I have to have p less than 50% for my HA to be true. Well, there's a whole lot of area up here that's above 50, so that is not true. So we cannot say the true proportion is less than 50% unless the entire interval is below 50%. So we would reject that it's less than. So we would we would keep HO, so we would fail to reject HO, and we would reject the HA, so we would not say that HA is true here. So technically, you guys, we should not compare a one-tailed test to a two-sided confidence interval. However, a one-sided confidence interval would actually move this confidence interval higher on the number line, making the area in red even bigger. And so I'm not worried about that at all here. All right, that's it. Bye.